me see. Okay. Okay, I think we can start now. Thank you, everyone, for attending session 2 of Navigating a Changing Arctic. And I'm Penny Wagner. I'm the head of the Sea Ice Operations at the Norwegian Meteorological Institute. And I'm very happy to present this session and be part of this session. This will be focusing on sea ice and iceberg monitoring and forecasting. And as you know, with this current state of the Arctic, this actually really strains operations a lot. And so forecasting is very near and dear to our hearts and very important for our end users. And we are looking forward to hearing some of these presentations. So I would like to first introduce our keynote speaker, which is Ed Blockley, who's the leader of the Polar Climate Group at the UK Met Office.
Right, let's make sure. Cool. Yes, thank you, Penny, and thanks for having me here today. As Penny says, I lead the Polar Climate Group at the Met Office, and we're in charge of polar climate research, but we also are in charge of the sea ice model development that we use for all Met Office modeling, including forecasting. So I'm going to talk to you a bit about some work I've been involved with for many years with colleagues at primarily in RV, about the sea ice drift forecast experiment, SIDFEX. And I'm particularly mentioning Helga Gosling and Valentin Ludwig from RV there, who I've got some slides from. So very brief outline of the talk, I'm going to talk a bit about SIDFEX and what Met Office has done in SIDFEX, and then how we've progressed to provide operational support from SIDFEX using the sea ice drift forecasts. And then a little bit about some science that we're doing with these forecasts, looking at deformation of sea ice. But I thought I'd start just this animation from Ron Kwok, now almost 25 years old, from the Sheba campaign, but it just really shows some of the challenges that we as sea ice modelers and forecasters are facing, trying to predict where sea ice is going. And this square of sea ice over this 6-month period, you can see it's just completely deformed, and you get these crazy deformation events. And you look at that and you think, oh, how are we going to model that? So with that in mind, I'll talk about SIDFEX. So SIDFEX it was primarily built around the Mosaic campaign, and you can see down the bottom here, there's lots of people involved in SIDFEX from many different countries and organizations whose flags and logos you can see here on the slide. And particularly highlighting Helga and Valentin there from RV. So the original motivation of SIDFEX was about intercomparison of sea ice drift forecasts, but the original motivation was where could RV park the Perlage Stern icebreaker to start the Mosaic cruise so that we could stay in the ice, or they could stay in the ice for as long as possible. And this plot on the right from Thomas Krumpen is showing, if they just looked at climatology, this is the star is where they could put Perlage Stern, and all those little trajectories are what the drift would have been from that point from all of the previous 10 years. And you can see there's a massive difference. Some of them come out through the Fram Strait in 6 months. Some of them are still circulating near the North Pole after a year. So they really wanted some forecasts. And we're producing Lagrangian forecasts of point assets, and we're assessing model skill by looking at these buoys and how the buoys drift. And then we subsequently moved on to provide semi-operational support to support the Mosaic cruise. So this is just a brief overview of what SIDFEX was to start with. So we had this sort of preparatory phase where we're developing functionality and just working out whether it was good enough. I'm going to talk a bit about that now, and then I'll move on to talk a bit about the Mosaic drift and how we supported that, and then some of the scientific legacy. So what we do in SIDFEX is we have this list of targets that are as a subset of generally the IABP buoys. You can see on the right there all of the buoys that were reported in the Arctic, I think at some point in January this year when I put these slides together. And we choose certain ones that are in strategical areas, and sometimes we will choose ships or assets that we know are in the Arctic and we want to provide support for. And those locations are made available in real time, and as the SIDFEX community, we produce forecasts, and there's no method. You can do whatever you like to produce your forecasts. Most of them are model forecasts, and it's up to you what you do for forecast length or ensemble size. But the format is regimented by SIDFEX, and you upload your forecast to the German supercomputer using this format here. It's an example forecast there. So it's just an ASCII file. And in the Met Office, I've been providing these forecasts for quite a while. Now they're an experimental forecast, so they're not operationally supported, but I've been contributing them myself, using a few of our systems, our coupled global system and our short-range ocean analysis system, FOAM. And we provide those largely in near real time, within a few hours of validity time. And actually, for the more technical, I use this Ariane particle tracking package to trace, using our daily sea ice velocity, just to trace where the buoys would drift to. And you can see on the right there example plots of some drift trajectories that are calculated using my method. Back to the sort of wider SIDFEX. You can probably see better on the side screens, but this is over the last 6 or 7 years. We generally had an increasing number of forecasts. You can see 2007 there, we started off with 2 or 3 forecasts per day. The black is the total number of forecasts, and then the red are the forecasts that arrived in near real time. So that wasn't the original focus of SIDFEX, but then people like me and the operational centers started just sending through these operational forecasts. And so we decided that we should create an operational forecast to support the ship. But we still have this big database of forecasts, and we'd be interested to collaborate with people if they're interested to be involved in them. And as of January this year, we have 224,000 forecasts there, nearly 300,000 trajectories in the database. And I optimistically have been putting Gosling et al. In prep on these slides for a while now, but Helga is leading a paper that should be being submitted later this year. So back to the evolution, and I'm going to talk a bit more about what we did during Mosaic and how to supporting the actual drift operationally. So the first thing that Helga did actually was to create these consensus forecasts. We've got up to 10 or 12 different forecasts from different places, and so we create a consensus from them, just from what's in the database. And so what Helga did was he threw away those in red here, anything that was initialized too long ago or didn't go far enough into the future. Those are the red lines. And then we sort of blend them together. So an older forecast, like the one featured along the top line here, we change the position, so it's like a relative drift forecast. So we say, you know, if this forecast did start with a ship in this location, what would the drift be? And they all get aggregated together to create this consensus forecast. So Mosaic was the primary operational support story for SIDFEX. That's why SIDFEX was created initially for this section here on the left, which was initially we were just informing RV about what would be an optimal starting location for the Mosaic vessel. But then we moved on to do these other two items in the middle and the right. SIDFEX forecasts were used daily on the ship for drift predictions, and in particular they were used by the guys at DLR in Germany to decide what TerraSRX images or high-resolution radar images that they would need to get processed from the satellite. Because you have to, 2 days in advance, you have to register the location at which you want that image, and it costs a lot of money to process. So the SIDFEX forecasts were used for that. And here's an example on the next slide of, sorry about the green, I'm not sure where that came from, but this on the left is an example forecast. It's showing the trajectory of, showing the trajectory of the ship compared to the forecast. So they're actually pretty close, and then we also include these 90% ellipse confidence regions as well. And so that was an example of what we sent to Mosaic on 24th of Feb 2020. And then on the right is some post-analysis evaluation. So this is the mean error distance, the distance error of our forecasts over that period from October to July during the Mosaic cruise. And you can see really that the thing to beat here are these big black lines at the top here, which are the persistence forecasts. So if we didn't exist, and you either persisted the location of the ship or extrapolated the current drift of the ship, you would get those black lines up there. And this line is actually a persistence forecast as well, so it looks similar. Whereas these are our forecasts collectively down here, much lower error, which is nice. And then this dotted line is the consensus forecast that Helga created and his sort of Frankenstein forecast, merging all the other ones together. And it's nice to see that, you know, that was even more skillful. And essentially DLR said that because of the SIDFEX forecast, their hit rate for these TerraSRX forecasts was 80 to 85%, and they were expecting more like 50% when they started on the campaign without our forecasts, they thought. So that was nice. We were not expecting them actually to be quite so impactful. So then we've been doing other things and supporting other campaigns. Forgive me, this is Antarctic, but this is, oh, getting all my buttons confused again. This is Endurance 22. Almost 2 years ago now, they found Shackleton's Endurance in the Weddell Sea there, and we provided support to them from SIDFEX in two different ways. We provided operational forecast, so they had the ship down here in the Weddell Sea, and they deployed an AUV to obviously search for the Endurance. We provided forecasts in real time, near real time, that they can use to work out how much their ship was drifting compared to the UAV. So they didn't lose contact with it. But we also provided information beforehand on the likely drift events that were happening in and around in that area. And we did that using this very simple picture here, which is we had these synthetic buoys that we pretended were in their search area, and we provided forecasts for them for many months beforehand, so they could get a lay of the land, if you like, and see how the sea ice was moving. Yes, this hasn't come out fantastically, but the point is here, we've got loads of forecasts, and their requirement on the right here was that an accuracy of 5 kilometers error after 2 days. And we met that actually in more than 60% of cases. This is the two-day lag here, and you can see that just over 60% there. But actually we're nearer to 100% on 1 day, which is nice. We were not confident, as I said, when we started in the Arctic, that we would be able to get good forecast of the pack ice. We were even less confident in the Antarctic. So it was really nice to see these results and to get good feedback from Endurance 22. And Valentin tells me that the Endurance 22 people people on that research cruise are still contacting Avi and asking for SIDFEX support for other cruises, which is nice. So there she is, the Endurance. You've probably seen this on the news. Very well preserved, because the waters are too cold for wood-boring bacteria to have survived in. And this at the top left is the last forecast that we sent them before they finally found her. So they were very pleased with the forecast. So I'm just going to talk a little bit now about this final block in the diagram, post-Mosaic legacy, what sort of things we're doing at the moment. As I mentioned a few times, Helga's writing up a publication about SIDFEX generally, and another about operational support of Mosaic. But I'm going to talk a little bit about some work that Valentin Ludwig is doing, looking at deformation of the sea ice. And firstly, I'm just going to scare everyone with this video again, showing just how difficult deformation is of the sea ice. And you can see occasionally you get these big events. You get sudden deformation of the ice. It moves around. And so we're interested in how the models do representing that deformation. So as part of the Mosaic, there was this thing called the distributed network, which actually Benjamin Raab has got a paper and review about at the moment. So we put these buoys, actually I was nothing to do with it, Avi and collaborators put these buoys around the polar stern Mosaic. They're generally about 35 kilometers apart, so they're quite a close network of buoys that they could actually get to from the ship by helicopter generally, and have observations more in the wider field. And so we are using those to derive deformation at that local scale. And then we use the wider SIDFEX targets, which cover the whole Arctic domain, to look at what we're calling Arctic basin scale deformation. This is just a picture here on the right showing how that distributed network moved with the ship all the way from the North Pole out through Fram Strait. Well, not quite out through Fram Strait, I think it took it apart a bit before. And so you can sort of see here, see better probably on the far side, but So Valentin produced these plots looking at the large-scale deformation and the small-scale deformation. This plot is large-scale deformation, and we've got total deformation at the top, and we've got normal shear along the bottom. And the models, this is our model from the Met Office 10-kilometre atmosphere coupled model, 1 day lead time. And the correlation is actually very good for divergence, and both for pure and normal shear correlation there, 0.69, 0.81. Valentin put p-value 0, but I think there's a truncation there. It's probably smaller than 0.001, so it's and then if we look at the small scale deformation, there is still some skill, which is nice. We're not expecting to do so well with small scale deformation with these sea ice models, which are designed for quite large scale evolution of sea ice. But we still have significant correlations there, the correlation of 0.54 up there for total deformation. But we're not doing quite so well for divergence, correlation of 0.18. But generally, the model is capturing the mean and the variability of the total deformation on the small scales, which is interesting. And we're looking at longer lead times here. This is still the same model, and the correlations do drop off quite considerably. These are all, this red line here is the divergence I was showing you before, and that really is the sort of outlier. It's a bit different from the other things. All the other things seem to follow the same evolution as we reduce the increase the forecast lead time. But these are still significant, the correlations there. So the model is still capturing things well, but the divergence not quite so well, which I think there are some assumptions in the sea ice model about tensile strength that I think may be contributing to that. And then just briefly, we have Valentin has produced this plot of various different models. So it's all the different, several of the different models that have provided forecasts for the distributed network. And you can see actually the pattern is pretty similar. This is just for total deformation now. At the small scale, correlation is quite good. And at the large scale, the correlations are considerably better. But the thing that interests me here is the grouping of the models. So at the small scale here, these three are all our models, in fact, in the Met Office. And they're all different resolutions. One of them's coupled, two of them are coupled, one of them's not. They're different resolution, but they're behaving actually in the same way. Likewise, the two Canadian models here, one high and low resolution, are behaving the same way. And when we move over to the large scale, you can see similar but reverse situation where these two Canadian models are doing better, but they're almost identical to each other. And likewise, our models are a bit lower. So there are some interesting differences in the sort of resolution versus the structural differences here. That it looks like the way that the forecast systems are created is perhaps more important in this case than the resolution. So this is some ongoing work that Valentin will be publishing this year, hopefully. So a little bit about that deformation, just a reminder, summary. We've compared the observations with deformation that we've derived from the actual movement of the buoys. The models are doing a bit better than we'd hoped and we'd expected, particularly at the large scale, which is a bit more skillful. But even at the small scale, we have significant correlations, and the model is promising in the representation of small scale deformation. And then just to recap, I'm quite interested in the fact that the forecast models that do better for large scale and small scale are quite different, and that the model resolution is not necessarily playing much of a role there. So just to summarize the whole SIDFEX talk, we've been producing these sea ice drift forecasts as a community now for over 6 years, and we have around about 300,000 sea ice velocity forecasts in a database, and they've proven more skillful than, I think it's fair to say, than we expected at the beginning of the venture. And they have been used operationally to support several mostly research cruises in the central ice pack. both in the Arctic and the Antarctic. And we're now looking at some more of the science with the deformation analysis, which just shows some skills for the model, particularly at the large scale, and some interesting things to look at further. So that's SIDFEX. While I've got this platform, I also wanted to talk about a project that we're starting, an initiative we're starting in the UK. We've under the UK government, under the International Science Partnerships Funds, we're looking to improve our Arctic forecasting capability, and I'm leading a work package on model development, so we're improving our model and our operational forecasts. And the project is really focused not just on the model development, but also on collaboration with, understanding stakeholder needs and collaboration with our partners and our Arctic friends. So if anyone wants to know more about this, come and talk to me afterwards. But I shall return to the summary of this talk and have any questions on that. So many thanks.
Thank you very much. I can take one question. Nope, but that's great. I think as we go further, we'll probably save some of the questions for the panel discussion.
Yes,
so thank you very much, Ed, for providing a very good comprehensive overview on some of the complexities that go into these models, and also how they're useful in a really good case study. So next, I would like to present Raphael Groth, and he is a researcher at the Weather Forecasting Development Division at the Norwegian Meteorological Institute, and he's going to talk about some of the effects of sea ice in the weather forecast models.
Yes, thank you for having me and being able to present my work. So I'm talking about sensitivity of our Arom Arctic model that we are running here at Norwegian Meteorological Institute, which is derived from the model that we run in the Nordic and Baltic states domain, but just specialized for the Arctic. You can see an image. I hope you can see the blue outline here. That is the domain of the model that we are forecasting. And as you can see, there's quite a bit of ocean in there, and as well quite a bit of sea ice, depending on the season we are in. As we develop the model further, of course, the connection to the boundary, and that means to the ocean and the sea ice especially, are quite important, and something that we try to focus a bit on. Here are named some of my colleagues that I'm working with, Malte Müller, Yuri Batrak, and Thomas Laverne, who is more model from the sea ice modeling community, while Yuri and Malte and I are working mainly on the ocean and the atmospheric parts of it. So just the motivation for us. What are the Arctic challenges that we face regarding weather forecasting? You see on the plot on the right here, this is, as well, you can see the two domains. The lower one is as maps, that is the forecasting domain for the Nordic and Baltic states, and Arom Arctic, the one that I mentioned before. And with the dots and the coloring, you see an indication of forecast quality, more or less. That is a plot that was provided by Morten also in Oslo. And you see that there is a significant decline of forecast quality when we come to the further north we move, and there's several reasons for that. One of the major ones is that we don't have observations that far up north. Many of the observations are land-based if you don't go to remote sensing, and there is not that much landmass. We have some on the Arctic islands and on Svalbard, but the main stations are on the mainland, so we are relying on remote sensing to a big extent when it comes to the ocean and the sea ice, and of course that has its own uncertainty within it. Then of course the Arctic has its own weather regime. Whenever you are moving along the globe, different weather types demand different specializations or different optimizations in the models. And for the Arctic, for our model, the sea ice and the boundary to the ocean is one of the important ones. So in the past, we did a bit of research on sea surface temperature, and from that, we wanted to extrapolate and go on further to the next stage with the sea ice and see what is the impact of sea ice quality and sea ice input from the boundary on the weather forecast and as well the development of the forecasts. The experimental setup is we're using just a bit of the Arctic model itself. It's a non-hydrostatic model that we use with a 2.5 kilometer resolution and 65 levels in the vertical. We did 48-hour forecasts twice daily, 0 and 12 Zulu, but we had a 3-hour cycling, so the model is run every 3 hours just to forward it and have the data assimilation in between. We're using data from EEC on the boundaries. It has a surface model that is taking care of a lot of fluxes and interaction with the lower boundary. As now mentioned already, 3-hour cycling for data analyzation. We did run for a period from beginning of February 2019 to end of March. So that was our main area of study. And the experiment is still going on. I can only show some preliminary results because the model was just finished a few weeks ago. And we are still continuing with the runs. So the sea ice products, the main objective from us was that we compare different sea ice products as the input for the atmospheric runs and the weather forecasts and see what is the difference in between the outcome, especially when you consider what happens downstream, not just in the ice or in the marginal ice zone, but as well down in the mainland. And for that, we used 4 different products. We have the IFS sea ice product from EC, which is as well used operationally. Then we used a multi-sensor product, which is combining passive microwave and synthetic aperture radar data. That one is as well produced in-house. Then we had a product from University of Bremen using IMSR2 data, and Cyrano, which is well developed partly from the meteorological office, and uses as well MSR2, but in a different fashion. And with Cyrano as well, we could get some estimates of uncertainty. So the plan is actually to perturb sea ice based on Cyrano data. That was the initial plan, to create an ensemble with about 10 members, and as well doing deterministic runs with input from all the other sea ice products. You can see that there is some ice charts from all the various products for the same time, and you can see there's some differences. So what we want to see is how much do those differences impact weather forecasting. So for the first 3 models, we did deterministic runs, and then we created an ensemble to compare with. The general concept of the EPS generation is that we need an estimate of the uncertainty of the sea ice, and then we generate a random noise field. When you combine those 2, you get a sea ice perturbation. So this is a random sea ice field, which more or less represents the sea ice situation of the day, but should have some random variations in the areas of highest uncertainty. And then you apply that field, and you do that 10 times and run the model 10 times for the same time, and you see what is the outcome in the end from a weather perspective. So when it comes to noise, the most straightforward way to go is just using white noise and put a band filter on it, so you can more or less limit the spatial structures. That is something that we did for perturbations when it comes to sea surface temperature, but we found that this is not generating the noise pattern that we really would like for sea ice. So in the end, we ventured away from white noise and applied a pink filter. So we generate pink noise, and you see the formula for this. And in the pictures, you can see a bit more that the structures of those two noise fields are a bit different. So it's a much more homogeneous with white noise, while you have some more spots, or large-scale structures in the pink noise. And pink noise as well is you have a parameter where you can tune the noise to go to more fine scale or to a more larger scale perturbations as well. So it gives some additional variability in that sense. And the next challenge that we had when it comes to generating the perturbations was masking. With a lot of the parameters you have, for example, sea surface temperature or as well vegetation or snow, you can perturb and apply just a land mask. But for ice, it was a bit more complex because we want to generate ice in regions where there is no ice yet, but we don't want to do it over the whole domain. So we had to be careful not to generate ice too far south. And then it was the question on how can we mask the whole domain to actually create a realistic ice field. So we applied an algorithm where we mask everything where there is land, and we give everything free where there is ice already. But then we have an area close to the ice where we say if you at this spot you detect ice within a radius of, let's say, 30 kilometers of a certain amount or a certain percentage, then you give that point free, and otherwise you mask it, and it's considered for perturbations. This took some trial and error, but I think we came up with a solution that is working. And then lately, when you have your random field, you need to scale it somehow. In the beginning, we just looked at the uncertainty from Cyrano itself, but it was not quite satisfactory. So what we ended up with doing is that we generated a polynomial approximation based on the variability of all sea ice products that I mentioned before. So you can see that here on the right. This is the variability of the sea ice concentration based on all products when you compare them to each other. And below you see more or less how the sea ice concentration behaves depending on the concentration at that point. And then we just recreated that for the ensemble. So more or less what our ensemble now reproduces is the variability between different ice products that we have. So this is now some preliminary results. Here you see the standard deviation of 2 meters temperature. And you can see on the left, this is the initial point, and then 24 hours after. And you see that variability in temperature now kind of spreads out from the sea ice and is well transported downstream. And we hope to see similar and good results in the future. Thank you for your attention, and I'm happy. If there's I think there's no time, but we keep that for the panel. Up to you.
Thank you, Raphael, for the presentation. I think, I'm sorry. I think we will save any very good questions for the panel discussion. I prefer. Thanks. Okay, thank you very much. Next, we will have Daniel Beaufort as a researcher from the European Center for Medium Range Forecasting, and he will present on the ice cap.
Yes, thank you. So I will present our efforts on a software tool which is meant to help users of sea ice forecasts to make more informed decisions. And it has a catchy name. It's called IceCap. I won't go into detail how this comes to this name, but I will show some of the capabilities of IceCap in this talk. Before doing so, I want to have a quick motivation why we do that. So there are a lot of sea ice forecasts around, even publicly available through CMEMS, like short-term forecast or seasonal forecast from the C3S archive. However, the user uptake is still quite poor, and there are many reasons for that, but some are, for example, that forecasts have deficiencies in quality and presentation. What I mean by this is that we know that our raw model forecast output often needs calibration to make it meaningful. Like if we have long long forecasts beyond 10 days, the model error growth, and then we have to calibrate them to make it meaningful for any users. This can be complicated and needs a lot of expertise the user usually don't have. A second one is that users also need information on uncertainty, and a lot of the information provided usually don't provide that. Also, another point is that end users ask for specifically tailored products, which can be quite different to what we have on scientific side, like what we usually look at. So this stimulates the co-development of the products between users and scientists. And another point I want to mention is that users especially ask also for information, not only for the next couple of days, but something between days and seasons ahead. These all points are meant to be covered by the software tool called IceCap. And IceCap is developed in a European EU Horizon 2020 project, Axiberg, which is now first year in, so it's another 3 years to go, so there's still time for development, and I'm in the middle of it at the moment. So I will not show all the capabilities, but I will give you a glimpse of what it can do. My first example I want to show is based on a real-life example in 2021. There was this, in late October, early November, there was this rapid sea ice growth, and a lot of the shipping industry was taken by surprise. So we had a lot of vessels which were stuck in sea ice and had to be freed after several days or even weeks, I think, by icebreakers. So when I started this job like a year ago, my first idea was like, what about the forecast? Was the forecast that bad? Because if you would know that this would happen, you wouldn't go there with a ship, I think. So I looked into the forecast, and in this instance, I used the forecast from ECMWF. It was initialized on the 7th of October, 2021. It's a so-called extended range forecast, which means at ECMWF it runs out for 46 days. It got 51 ensemble members, which provides some estimate of uncertainty. And what I did then, I choose a point in, which is here the red dot. You can barely see it, I know, but it's in the Russian Arctic. It's very close to one of where the vessels got stuck in this year. And what I did then is I calculated the distance of that point to the sea ice edge for observations and for the models. And the result you can see here on the left-hand side. So on the x-axis, you got the forecast time. So 0 means it's the 7th of October 2021. And on the y-axis, you have the distance to the sea ice edge. Please first look at the black curve. That's the observations. And you can see that in the beginning, the ice edge was about 180 kilometers away. And then the ice grew and came closer. And then around day 8 to 10, there was a really rapid increase. And you see the distance was getting very close, like 25 kilometers. And at around day 15, this point was stuck in ice for the whole season. The blue lines now show you what the model is doing. And each of the thin blue lines is one ensemble member, and the shading gives you shows you where most of the ensemble members are. And this is really the raw forecast output as we have it from ECMWF. This is why I call it now uncalibrated forecast. And you can see the forecast general behavior is very similar, but you can also see that there are, especially around day 10 to 20, there are really differences. Like the model predicts a much slower sea ice growth, which means that this point location is stuck in ice only around day 25 for most of the ensemble members, which is like 10 days later than what was observed. So obviously people might think, okay, that's not useful because in 10 days I'm through this area. But as I mentioned before, on these timescales, longer than 10 days, we know that we can have large model deficiencies, and we have to correct them. What we can do, and what we usually do, is we use past forecasts and calculate how much was the error in the past, and then we subtract that error and generate a so-called calibrated forecast. And this is what I've done here. So here I use the forecast for exactly the same calendar day, so the 7th of October, but from the years 2016 to 2020. So 5 years, and for each of these years, I calculated the distance of that point to the sea ice edge in observations and the models, and I calculated the mean error. And that mean error from these 5 years, I then used to calibrate the forecast for 2021. And the results you see here in this graph, the black line stayed exactly the same. Obviously, it's observations. I can't change this. But the blue line is now the calibrated ensemble. And you can see now that this one is much closer to the observed sea ice edge distance. And it's maybe off by still a couple of days, but I would think that's probably quite useful. So if we take into account those errors, then we could have forecasted this event quite good, I would think. And this is one example of what IceCap can do. You don't have to care about all the background, how all the software works and how it is calculated. You just basically tell it, I want to have a sea ice distance. This is my location. I want to have it calibrated with number X years, and it will provide a plot axis. I have a second example. This is from very recent now. So this is the latest seasonal forecast from the German Weather Service issued on 1st of January this year. And here I look into something completely different. This is the date of the retreat of sea ice. So the last day of the season when the sea ice is above 15%. And obviously, we do not expect a seasonal forecast model to predict exactly the observed date when this will happen this year, right? But what we can maybe expect a seasonal forecast model to do is to predict in how far this year we expect an early or late breakup of the retreat of the sea ice. And to do that, it's very similar to what I've done before. It's like I used from the same model the January forecast from 1993 to 2016. For each of these forecasts, I calculate the date at which time the sea ice retreated. And then I calculated the same for this forecast, so the actual forecast, and then just look in how far the actual forecast date of retreat is later or earlier than normal for this model. And this is what is colored here. So basically, when you see red colors, it means that there's a high probability that the sea ice will break early, or it is predicted that there's a high probability that the sea ice will break up early in this area. So examples are, for example, the Bering Sea here. And the blue regions is where there's predicted to be a high probability of a late breakup of the sea ice. And you see that this is the case for the North Atlantic and part of this Sea of Okhotsk. So just to summarize, some take-home messages. I hope I can show that this IceCap is really developed to help users to make informed decisions by drawing on different sea ice forecasts available. It can handle forecasts from days to seasons. And now people might say, well, it runs on its local computer. It doesn't help me that much. That's right. But in the course of this EU project, we will implement IceCap on the Wikio platform. And the Wikio platform is really an entry point for users to have all the sea ice forecasts available by hand. And you do not have to care about the infrastructure and everything. It will all be in the background for you. You just have to run the IceCap software, and it will provide you with some graphical information. We have already implemented some prototype products, for example, this distance to ice edge, what I showed you, but there's still around about a year of development of this tool, so if you have any suggestions, I would be happy to hear them and see if they're feasible to put them in. I didn't touch on this in this talk, but IceCap is not only designed for users, it's also like really a tool which can allows the scientific model developer to verify the sea ice forecast with a thorough skill of assessment. If you have any questions for that, just get in touch. Thanks a lot.
Thank you very much. I think, yes, I think we'll save the questions for afterwards if that's
Perfect.
okay, but thank you very much for such a great presentation as well. Okay, thank you. I'd like to now introduce Abigail Dalton. She's an emerging geomatics specialist at the Natural Resources of Canada and the University of Ottawa. Abigail, are you online? Should we join us?
I'm online. Can you hear me?
Yep, we have you. Great. Yes, and Abigail will be presenting on the iceberg ship coexistence and in the Canadian Arctic. Great, thank you.
Great. I'm assuming you can see my slideshow. Okay, so I'll just get started. So thank you for the introduction. My name is Abigail Dalton, and I'll be presenting today on some of the work that I've completed during my PhD thesis last year. So I wanted to start just by providing a quick overview of shipping routes throughout the Canadian Arctic. I'm sure you've all seen a map similar to this. But you can see here that in the Canadian Arctic, ship traffic is concentrated largely through Hudson Strait, along the east coast of Baffin Island, and at the beginning or the entrance of the Northwest Passage, and then also into the Canadian Arctic Archipelago. And what this map also highlights in the darker blue shade is the lack of reliable bathymetric data in the Canadian Arctic. So that limits vessels to where they can safely navigate. So here's another map, which is focused more on the Eastern Canadian Arctic. And this shows all locations of ship and iceberg collisions since the year 1800. So sure, that spans over 200 years. But here are all of the ship and iceberg collisions that have occurred since 1980. So in this case, a collision can include anything from a denting to a puncture to sinking of a vessel. So in part one of this session yesterday, there was mention of the Polar Code and also Polaris, which is a risk index for ships navigating through the Arctic. And so although icebergs have been widely identified as posing significant hazard to ships operating in the Arctic, very few formal recommendations exist about navigating in iceberg-infested waters, with the exception of planning routes through polar waters that take into account current extent and the type of icebergs in the vicinity of that planned route. So of course this is a good idea. However, ice charts produced for the Canadian Arctic tend to broadly classify iceberg-infested waters as bergy waters, with little to no information about iceberg size, shape, or specific location. And more specific iceberg charts produced by both the Canadian Ice Service and the International Ice Patrol only cover the areas south of 60 degrees north. So the lack of inclusion of icebergs in current navigational risk assessments, in combination with the remoteness of the Canadian Arctic, limited search and rescue capabilities, limited bathymetric data, those all highlight the need for improved assessment of potential risk of icebergs to navigation. So where are the icebergs? So we have a general idea of where icebergs drift, given ocean currents, wind currents, bathymetry. But in the Canadian Arctic, very little research has been done, either on a large scale or on a more local scale for iceberg drift tracks. So tracking icebergs using satellite imagery can be difficult, given spatial and temporal resolution of imagery, and also the ever-changing geometry and location of icebergs. So part of my work during both my master's and my PhD was deploying about 50 tracking beacons onto icebergs, which then contributed to the Iceberg Beacon Database, which was a joint project between Carleton University here in Ottawa and the Canadian Ice Service. So there's also the Canadian Ice Island Drift and Deterioration Database, or CI2D3, and that contains thousands of locations of ice islands, which are large tabular icebergs, and ice island fragments, in synthetic, and those were detected in synthetic aperture radar imagery. So for my project, I used these two data sets to create a climatology of icebergs in the Eastern Canadian Arctic to give us an idea of where icebergs are known and have been observed to commonly drift. So the figure on the left is showing the distribution of icebergs from the beacons that we deployed and others from the Canadian Ice Service from 2012 to 2019. And on the right, we have the distribution of ice islands and ice island fragments from the CI2D3 database from 2008 to 2013. So what's true for both data sets of observations is that icebergs tend to drift through Nares Strait between Ellesmere Island and northern Greenland, along the coast of Baffin Island, including, again, the entrance to Lancaster Sound, and which is there in that circle, and then oftentimes into Hudson Strait. So icebergs are a complicated topic in the Arctic. So on one hand, yes, they're objectively a hazard. They can do damage to a vessel, particularly one that isn't ice strengthened. On the other hand, a large number of people every summer pay for passage on cruise ships and passenger vessels where icebergs are advertised as a feature that they're interested in seeing. So questions around Arctic shipping are difficult, and it's difficult to decide what ships should and shouldn't be allowed to do. So right now, we have limited information on the known locations and drift patterns of icebergs. So the first step before someone can decide, what is a risk and what's not, is to simply just understand the overlap in spatial distribution between icebergs and ships in the Canadian Arctic. So that brings me to vessel traffic, so where ships are located. So most vessels operating in Canadian waters are equipped with AIS transponders. So in the Canadian Arctic, the shipping season is typically from about July to October. And during that 4-month period, we found, using AIS data, that from 2012 to 2019, the number of unique vessels operating in the Arctic more than doubled, from 108 in 2012 to 271 in 2019. And over that time period, the number of trips taken by those vessels also increased from about 6,500 to nearly 11,000. So these figures now show the spatial distribution of vessel trips for all types of vessels. So for the earlier time period, 2012 to 2015, and then in the later time period, 2016 to 2019. So what's clear is that traffic along the east coast of Baffin Island has increased. Also into Pond Inlet and the entrance of the Northwest Passage, which is located here, and through Hudson Strait. So looking specifically at different types of vessels, so for dry bulk ships, here is the spatial distribution over the 2 time periods. So this shift in the number of trips being taken coincides with the opening of the Mary River mine on Baffin Island, which is located here at this red triangle. So this mine opened in 2015 and reached full operation in 2018. And because the mine operates year-round, but shipping traffic is limited to late summer, there's a large amount of traffic in this area during the shipping season. And next, just looking at passenger vessels. So we can see that the number of trips surrounding the entrance to the Northwest Passage has increased, and that shipping has also generally shifted northward. It's worth noting that passenger vessels typically have little to no ice strengthening. So this movement northward and into the Northwest Passage has the potential to pose problems not only for icebergs, but for sea ice navigation as well. So for this study, we used the previous 2 data sets, so the iceberg climatology and the AIS data, to create an iceberg ship coexistence index, basically by multiplying the unique number of icebergs by the number of trips taken by a vessel in any given 50-kilometer cell in this figure. And so what we found was that some of the greatest increases in coexistence of ships and icebergs occurred for dry bulk, cargo, pleasure, and passenger vessels. So coexistence, again, increased along the coast of Baffin Island and into Lancaster Sound, with coexistence moving northward into Nares Strait, for both pleasure and passenger vessels, again, which typically have less ice strengthening than other types of ships. So in conclusion, we found that shipping has increased through most regions of the Eastern Canadian Arctic since 2012, largely along the route of the Northwest Passage. So this photo on the right is the Crystal Serenity cruise ship. It's docked near Uglukaktok in the Northwest Passage during its 2016 trip, where there were more than 1,000 people on board, which is more than twice the population of the community. So this cruise ship normally operates throughout Europe, the Caribbean, and Asia. So while this voyage was an anomaly, smaller passenger vessels, smaller cruise ships, typically, again, with little to no ice strengthening, have begun to operate with regularity throughout the Eastern Canadian Arctic. So while there are, of course, economic benefits to increase tourism in this region, on the other hand, if anything were to go wrong, ice-related or otherwise, the infrastructure, search and rescue capacity within the Canadian Arctic is currently very limited. So this really highlights the importance of continued and increased monitoring of all types of ice conditions in the area. So with that, I thank you and happy to take any questions at the end.
Thank you very much, Abigail. That's a very nice presentation. And next, we're going to continue on to the Asseyburg We're going to hear more about the Asseberg project, and I would like to introduce the research director of the Nansen Environmental Remote Sensing Center, Laurent Bettino.
Thank you. So, next it says, so yeah, you've heard Daniel about the Asseberg project. He presented one aspect of it. The Asseberg project is about sea ice and icebergs, and I really hope that Abigail stays online because we have say a few questions for as part of this presentation. So I have Laurent Bertino. I have the honor of being the coordinator of this project. And so the starting point is, say, an article that Penny authored a few years ago, showing that there's increasing say activity in the Arctic generally, and so some routes are getting more busy, and the ice is retreating from these routes. Then there was this incident that Daniel mentioned earlier about ships getting stuck in the ice and giving us these wonderful trajectories of sea ice. These are in situ sea ice observations, the most expensive probably, but their observations are on their own right. And so Daniel showed is that it could have been anticipated that these conditions could have become rough using the seasonal forecast. What later Malte has published, Malte Müller here, is that if they should really have checked the short-term forecast as well, because that would have saved them from trouble. And I'm not saying more than that. So the project aims to bridge, as Daniel said, a few gaps between the different forecasts at different ranges. And we plan to do that by using the forecast, bringing them into different platforms for validation. Wikio, which is this, centralized infrastructure for getting access to all the Copernicus data, and as well into iceberg forecasts, individual iceberg forecast. So first about the sea ice, we would like to use a bit better the information provided by passive microwave data, because these maps you see here are maps of sea ice types, multi-year ice versus first-year ice. Here from two different models, so Topaz 5, which is based on the size model, and NextSim, which is a very different types of sea ice model. And that comparison is fresh, it's from last week. And if the same comparison last year would have looked very different, but the gap between these models is closing progressively. So what we see here is that, well, there's multi-ice, mostly in where you expect it to be, and the passive microwave data, so that's from a different date, from AMSA2, also gives it information. It's just not utilized by forecasting systems. So that's something we'd like to do progressively as we move after the Asseberg project by assimilating the data in its, say, the raw format, which is a level 1 brightness temperature. So this is the activity of Marina Duran-Moro in Oslo, where she's trying to assimilate the level 1 brightness temperature. And to do that, she has to first emulate the observation operator, which is trying to do brightness temperatures as from the model data. So here, using all the auxiliary data that you can find about the atmosphere and the sea ice and the ocean, these are simulated brightness temperatures at the time and the location where the passive microwave data is available. And then next step will be to assimilate this data as different channels in brightness temperature. So we want to do that with the ensemble canal filter, the software that we use for the Topaz system. Next thing is icebergs. So we are developing open source iceberg drift forecast model that is part of the open drift infrastructure from Met Norway. And that open drift is used for all kind of drifting objects, which would be, say, oil spills as much as man overboard or search and rescue. Now this open drift can be provided to users using different platforms, using Halo, which is Met Norway's own platform for their specific users, but also it could be included into Wikio, which is what we will discuss in the end of this week when we meet with the Asseberg project on Friday. Those of you who would like to, say, know more about this meeting on Friday, you're welcome to talk to me and agree about that. Then, what we want to do is to calibrate an iceberg drift model. And to calibrate a model, we need, say, more than one iceberg. See what you see here on Novaya Zemlya to the right is just, a fake iceberg. It doesn't exist. But a collection of trajectories is immensely useful because that's what we need to feed our statistics upon. And so that's why, as well, the treasuries that the Canadians have collected, Abigail did collect in a PhD, are probably very useful for us as a project. So, as a summary, we would like to provide something that will be the first open source iceberg forecast, and people would be then welcome to try it out, use it on, say, the Wikio platform, on so the cloud servers that would not even be on their laptops if they want it to be. And then access to the forecast, seasonal and short-term forecast from Copernicus. And these would be validated using IceCap, as Daniel presented before. And then, if we want to think beyond the project, we need to go beyond the ice edge to look at dynamics of the multi-year sea ice. So we need to look back to what Ed presented earlier today on the deformations, because there's probably implications of that we need to consider. And then exploit the new missions from the European Space Agency, SIMR for passive microwave, and ROSEL for SAR in L-band, that need to be, say, exploited. And from that, we can get useful sea ice information and iceberg information. That concludes my talk. Thanks.
Thank you very much. No, can you hear me? Thank you very much. I will say you actually have a lot of time afterwards because you provided a very quick, comprehensive overview on a very busy project. So I'm going to allow you to have a question, just in case, while it's still fresh in everybody's mind. If anybody has a question on the iceberg overview.
Shoot on.
Okay, then build it up so we can save for afterwards. But that means you have to get a really good one.
Thank you.
A good and difficult one.
Yeah, open.
Okay. And then, so finally, I would actually like to present our last speaker for this session would be Wisław Myslowski. He's a professor at the Naval Postgraduate Academy, and he's going to be presenting. Can you hear us, Wisław? Yes, I think. Wisław? Testing. Okay.
Sorry, can you hear me?
Yes, we can hear you. Yes.
Okay.
Fantastic. Okay. Did you hear us? Yes. And then, so Wisław will be presenting on the advancements in subseasonal and decadal Arctic climate modeling. Thank you.
Okay, can you hear me?
Yep. Yes, we can hear you.
Yeah.
Yes.
Okay, thank you. So first of all, thank you for having me. Thank you for letting me to present remotely. Just wanted to apologize. I made it all the way to Oslo on Monday to find out that my connecting flight from Oslo to Tromsø was rescheduled until later this evening, so after my presentation. I would like to talk to you about the capability that we've been redeveloping at the Naval Postgraduate School in Monterey, California. It's a multi-institutional project that have been in works for over a decade now regarding regional Arctic system model. And I'll talk to you about some advancement we've made in terms of subseasonal to decadal Arctic climate modeling and prediction. So just a brief overview of the model. If I can,
Let me see. Yeah. Wisław, can you hear us? Sounds like it could be on his end. Yeah. Wisław? Hello? Maybe I should try to text. Oh. Wisław, can you hear us? Okay, so in the case of time, I am going to, I think that we may try to, we have about 15 minutes for the panel discussion reserved, And I would like to maybe start this, and then I would like to give Wisław the opportunity to present afterwards, if this is okay. So for the panel discussion, I would really like if we could have the speakers come up to the stage. And once we get Wisław back online, I'll catch him up of what we're going to do. Thank you very much. I was going to say, this does include you too, Ed. Yeah. Okay, thank you very much. So we may have more or less time for the panel discussion. In this case, we actually had so many fantastic presentations that we covered icebergs and sea ice forecasting. So I would, and real quick, Abigail, can you hear us? Are you still online?
Yep, I'm still online.
Oh, fantastic. Okay. I would actually first like to open up the floor to everybody else because we went through so many good presentations, and maybe somebody has a question to ask the panel first or individuals. So I would like to take questions, if anybody has any. We have one in the back.
Hi, James Lee, University of Liverpool. Maybe a question more for the icebergy people. I was just wondering if you're talking to any of the glaciologists who are looking at where the icebergs are coming from and how the iceberg carving processes are changing to try and understand where the icebergs are coming from at the moment that are posing a risk and how those risks might evolve in the future.
So that's one for me, yeah?
Yep.
So we're not yet using this information. We did use in the past, estimates from glaciologists about calving rates, and then initiate, say, probabilistic forecasts for, not for real-time forecasting, obviously, but more like for climatological purposes, knowing where were the years with lots of icebergs or little icebergs. So there's a paper that's dated 2009 about the Barents Sea using that. But yeah, we would like to take that further in the iceberg project and use whatever is on the shelf for, initializing this kind of risk forecast over long term. Yeah. So in last November, there were a lot of this work presented at ESA in Frascati during the Polar Week. But I don't really have an overview of all what is available from different sources. If there's one centralized source with all the information, that would be fantastic.
Great, thank you very much. Abigail, did you hear this question regarding the icebergs?
I think so, and I'll just chime in. So for our work, where do I start? Okay, so I think we understand largely where icebergs are coming from, like the main sources from the Canadian Arctic. That being said, ice discharge, solid ice discharge from glaciers in the Canadian Arctic is something like 5% of that from Greenland. So icebergs drifting in Baffin Bay are most likely from Greenland. That said, for our iceberg beacon deployment, we tried to focus on deploying on icebergs that we knew were from the Canadian Arctic, so right from the source, like near the terminus of each glacier. But again, it's likely that most of the icebergs from that database are in the Canadian Arctic, or sorry, are from the Greenland Ocean.
Okay, thank you very much. Ed, did you have something to add?
Actually, I had a question for Laurent about icebergs, if that's allowed.
Let's stay on icebergs.
It's my understanding that iceberg also had some remote sensing aspects of icebergs.
Yes.
Is that right? So,
yeah,
because obviously observations of icebergs is something that's a big deficiency.
Yeah, so that I can comment on that. So what we have as of today is a SAR-based product from DMI that mostly covers the south part of Greenland. So the plan is to extend that to, say, further north in Greenland. And our dear friends at Met Norway also plan to work on the Barents Sea. And for that, the main challenge will be to disambiguation of ships versus icebergs. So that's because, yeah, in Greenland there's mostly icebergs and few ships, but in Barents Sea it's the opposite. Mm-hmm. So that's the activities that will be ramping up this year, I guess, because I think there's, I will know more on Friday. Yeah. Yeah, you're welcome to join us.
Thank you very much. Okay, so actually, I have a question for the panel. It's a very overarching kind of question. And I think this fits into everything you all presented, but I would like to know, actually, in your opinion, how do you think we can have more ongoing intercomparisons that show the performance of these sea ice and iceberg models that, in a way that's actually relevant to users and all different types of users? I mean, we saw a lot of some of the physics and the engineering, but actually the visualization and the post-processing. How can we do this in ongoing, and what do you suggest? Let's start with you, Ed.
Well, in my presentation, I showed one such activity that SIDFEX started as a scientific intercomparison, but then we have involved users. We've used it operationally, but they're only scientific users. At this stage, they're mostly been, research cruises. It would be nice to go much further than that. There's two aspects. One is the the actual comparison. We need to set up some better machinery so the scientists can be comparing our products with each other, but in ways that are relevant for the users. So we need that information.
It's actually, and I'm thinking from the user perspective on how would they understand these products that actually resonates with, that's visually appealing.
Yeah, we don't want to just scare users off by sending them loads of products. We need to understand them, and we need to understand their requirements, and vice versa.
Yep, thank you.
You have any comments on that?
Laurent?
Yeah, I would say that SIDFEX was rather unique, that you could see the quality of your model in comparison to the other models on the same data. And we are usually not paid for doing that. It's maybe a pity, but there's no, there's clubs of, say, sea ice forecasters who meet and discuss in workshops, but there's no constraint for us to actually provide the validation data using a formatted, say, framework as in SIDFEX. So the dream now is that we can provide that automatically using the data that is available. That we can just extract the trajectories, calculate them all in a similar way, and then the next step will be to calibrate these data so that well, the users may not want to know why there's errors in our system, but may want to get the best out of it. And that can be calibrated as the work from Cyril Palerme did a few years ago by just post-processing. And that's for the drift, which I guess is ranking high up on the list of on the wish list. And then there's also the ice edge, and that's for, say, maybe for many more users. And that I count on what Daniel is doing to show the way forward.
Yep, I agree. Thank you. Daniel, would you like to comment?
Yes, I think for like this tool really has like what I presented has the strength that it can draw on different forecasts. So I only showed, for example, the season forecast from the German Weather Service, but actually you could take any of them. Like you could have a comparison of all the different forecasts for the same product. That would be very easy. And actually, this is what this tool intends to do, like filling the gaps so that the user can easily draw on different forecasts and then have the full image of what's available.
Thank you very much. Raphael?
Yeah, I mean, I see myself more or less as a user, and on the user side, I'm not necessarily one of the end users, but somehow an expert user, since we rely on sea ice data, but not producing it ourselves. But nevertheless, I mean, the sea ice or weather, they're both high impact components of traversing or working in the Arctic or just living there. So I think for us, if I might deviate a bit from your initial question, is that from a weather modeling perspective, it's when we talk about the Arctic, it's important not only to get a sea ice product with the best quality, of course, that is the main goal, but as well an estimate of its uncertainty, because that is something that we need to develop or estimate or tune our EPS systems.
Great. Thank you very much. Abigail, would you like to comment on this?
I think the panelists had great contributions. I'm not much of a modeler, so at all. But I think what's clear, though, is that the observational data remains very important, especially for something like iceberg drift, where there is quite a bit of uncertainty. And so, yeah, continuing to produce that and to be able to provide products and produce products that don't actually exist right now about iceberg locations and iceberg forecasting would be incredibly useful. And I think also that the other presenter is back online, so maybe...
Great. Yep, thank you very much. Wisław, I'm sorry, could you hear us?
Yes, I can hear you. I don't know what happened. Apology. Just Zoom dropped out of nowhere.
Oh, yeah, that's no. Sorry about that. So just letting you know, we fast forward to the panel discussion, and it looks like we've about 5 more minutes, maybe a +1 in the session. So we're right now talking about. The question was looking at what types of ongoing intercomparisons can be done to look at the model performance, but would you like to talk about this, or would you actually kind of like to do a hybrid of that and then talk about that during your presentation?
So the organizers suggested maybe my talk will move to the 4 o'clock session, and
Okay.
I'm happy with that.
Okay.
I can go either way, but if you want me to answer provide some feedback on the question about the products and uncertainties, I think it's important that we consider what timescales we're talking about those products, because those products' quality and their uncertainty will change dramatically if we're talking about short-term weather prediction relative to, say, beyond 2 weeks, sub-seasonal to seasonal and longer timescales. So the operational products or weather prediction sea ice products clearly require data simulation, because that helps and that provides some sanity check on the model in terms of constraints. When you go beyond, I don't know, let's say 2 weeks or sub-seasonal timescales, data simulation is not necessarily going to help you much, because you don't have data to simulate into the future. So if your model has biases over a longer time period, it will go back to the drift that it has originally, and your data simulation initially for initial conditions is not going to help much, especially if it's only a limited, say, ice concentration instead of a full ice thickness distribution. The other thing I wanted to mention that I believe is something that will become more and more important in terms of sea ice products is sea ice deformations, especially divergence and convergence. Some of the speakers earlier yesterday discussed the importance of adjusting the ship track to available network of leads and ice cracks, basically, in order to save time and fuel. But those deformation fields are hard to predict. They are very small scale, and they require very high temporal resolution as well. I'll stop here.
Yep, no, that's very great, and this is something that we agree with as well from the operational perspective. Can I open up, because we actually have a few more minutes in the panel session now, since your presentation will be moved to the next session. Would anybody like to ask a question to follow on this topic? Yes.
Hi, Dylan Jones, University of Portsmouth. What I'm trying to do is a very long-term prediction about the passages, the Arctic passages, and when they might be available. So my question is it possible to get any kind of accuracy on predictions in the timescale 2030 to around 2060, or should we just be using scenario analysis because the technology doesn't yet exist for that?
Well, I can say something. I mean, the climate scenarios that we have are projections of climate, and one of the biggest uncertainties in there is what the CO2 emissions are going to be. And so that's why with the climate modelling we have lots of different scenarios, because we're trying to paint that broad picture of what the future could look like depending on what CO2 emissions or other land use changes that other anthropogenic contributions are to the environment. So there is some decadal prediction skill. There are some aspects of the system that have long-term predictability that you can get some skill on decadal timescales. So maybe there's a blending of that information, and actually there's a bit more of a focus of that in the next round of IPCC, that we might do some more short-term projections. But I don't think anyone here is going to say that we're going to do, those lengths of prediction, but the uncertainty is very big, so you would need a big ensemble and really make sure you're trying to capture all of the uncertainty. It's quite complicated.
Would anybody else like a comment on that? No. Okay. How much more time do we have? Am I correct? It's 30 seconds?
Correct.
7 minutes. Oh. I think this is wrong then. Oh. You have a question? Okay.
I can shout. So,
I think you have a microphone coming.
hi. Great presentations. I'm nowhere near the modeling systems, and my PhD is in marine microbiology, so I was just wonder, and apology for my question, how easy is for us, for example, researchers that actually go on icebreakers, on research vessels, to use your modeling programs, to see just one page, to go the script and the outputs like, oh, I understand this, not doing those specific language.
I didn't catch all of that. So how easy it is to go out on the ice from an icebreaker?
For us, for example, people that don't understand about modeling, just simple language.
So how easy is it for a
Yes.
non-modeler to interpret and model forecast? I mean, that's a good question.
Well, I would say you need to get used to that before you're on board, because with the connections you will have in the field, you'll have little data available. You can trust different variables of the model at different level of trust. So you will need to find the documents that explain what has been validated and how, and then you will see that, well, concentrations and now the metric that's been used a lot is this IIEE, integrated ice extent errors. It will tell you how many kilometers squares of errors you will find between a model and reality, meaning that you can be here, the ice edge can be there, or maybe plus minus 40 kilometers to find the ice edge. Then when you're already into the ice and you're doing microbiology of sea ice, you may want to know about the thickness of the ice and what type of ice you will find. This is getting to a second level of difficulty in that very few models will actually constrain the ice thickness, and the observations of ice thickness are very uncertain as well. So there's experts in the room that will tell you all about it. So then you will know that there is some multi-year ice and first-year ice in the area, but then looking out the window will tell you that already. And then the age of the ice may be of importance. That information is available and can be used as a guideline. You will have an ice pixel average estimate of the age of the ice. It will not give you the whole, histogram of what's the age of different flows of the ice, but then you will have still an indication you are likely to find old ice or young ice compared to the surroundings. So that can be more a guideline if you want to, plan an expedition and you don't know on a 1,000-kilometer scale where you're going to go, then the models will tell you that the thick multi-ice will be concentrated into the Fram Strait. Go there, you'll find it. But normally people around you will know that information before. Yeah. But it's still good to actually, the people are in the field and try out before they set out, and then they give us some feedback whether the thickness was 1 meter off or half a meter off. It's good for us to know. Yeah.
Thank you. Yes? Oh, no.
The microphone wants to be
Right
back.
here.
Hi. It's just a follow-on question to that, actually. It's, how would a user or potential user know what to look for and what model to look at or what forecast to choose? And how would they understand what the accuracy and confidence they should have in that information?
Maybe Daniel would.
Yes, I think so. Obviously, we're talking a lot about like user products, but a product always comes along with the verification of that field. So if you do not know how good the model is, you don't know if the product is any valuable. If I show you something and say, oh, well, it's going to be ice-free next month, but the model does never predict ice in that area, then it's useless. So I think every good product should come with that. So if someone wants to use something, and let's say you have 5 models and you don't know which one to pick, there should be always like 5 products and 5 verification scores. So basically showing you, okay, this model is that good as this, or is better in predicting that variable compared to this model. And then with that, you basically know which one is the most reliable in terms. I think that is something, well, should always be, like the product should always be accompanied by something like this verification metric, if you want so.
Yeah, we put a lot of efforts into our validation reports. They may not look nice, but please let us know if you don't find the information you want in them. Yeah.
Can I actually extend on that one, though? How would you suggest that we look at these uncertainties of the products that are being assimilated into these models, or like the data assimilation and these different like remote sensing or derived products? I think this is where we find a lot of these challenges are at.
Yeah, I think that's certainly an issue for our forecast. Our forecast does look very, very much like the satellite data that we assimilate, the passive microwave satellite. But as Laurent was showing earlier, that there are significant differences between lots of different satellite data.
Yeah, exactly.
and we've actually had this issue with model comparisons in the past, where we've tried to compare our forecasts, and the satellite data that you use to compare them all can make some look better than others, depending on whether that's the one that they've chosen.
Yep.
So you do have to understand the uncertainty in the data sets, and you can try and assimilate them all at once, or as Laurent said, go back to the more raw data and make those assumptions yourself.
There's a biodiversity of modeling, because there's no old singing, old dancing model today. So Ed's model will use a different forcing field as the other models here. We mostly use ECMWF. Ed has the UK Met Office. So that's a difference. How much difference that plays on the rest of the system? Well, you can see from the ice drift, for example. Then it's hard to get to know from someone who's external where is the, where to find the information that you're looking for, and then forget about all the rest. So for that process, you need to actually get in contact with the producers and ask, okay, I want to do this. Please advise me. And there's nothing that beats that human communication.
Daniel, would you like to provide? Oh.
No.
I thought you were about to say something.
No, thanks.
No, I agree. Actually, it is really important that we have this communication. But I think it's I'm really getting at, so that we have a lot of these remote sensing products. But if we're in the case of short-term sea ice forecasts, we're looking at something that's actually representative of the actual ice conditions and not climate, I guess, for that matter. Just because to make very strategic decisions, how do you suggest that we kind of look at these types of uncertainties? Because we'll be looking at different types of models, like the other products that actually go into these models normally.
Sorry, I was just looking at this poor
0.
woman is waving that sign around.
Just a quick yes or no.
Yeah. Soon you'll get ensembles.
Yes.
You may not trust the numbers of the uncertainties, but you may trust how they evolve and qualitatively where the uncertainty should be.
Yes.
And if you can have an multi-model ensemble as well, then you get even more spread. And that's the sort of thing we've done with SIDFEX, for example, or I guess Daniel was wanting to do with IceCap. You can have lots of different models. You can then really get an idea of like potentially how wrong each one could be.
Yeah. No, we look forward to seeing this as well. So, anyways, but thank you so much for your participation, your presentations. And Wisław, we look forward to hearing you in the next one. And thank you, Wisław and Abigail, for participating remotely.
Thank you.